Exercise 183, page 462, question number 6a, integrate between 1 and 2, cosec squared 4t dt. If we look at the function y equals cosec squared 4t, we note that it goes off to infinity between 1 and 2. So although we can find the area underneath the curve, it's going to be one that we've got to be a bit careful when we come to apply this to an engineering model. But let's carry on with the question and work out what it is. So this is a standard integral, and if you look in the standard integral text, you'll see that the integral of cosec squared ax equals minus 1 over a cot ax. So integral of cosec squared ax with respect to x turns out to be minus 1 over a cotangent ax plus c. So that's the standard integral that we're going to use in this case. So what's the integral we have to do? It's integral between 1 and 2 of cosec squared 4t dt equals, so we can, it's minus 1 over 4 cot 4t between 1 and 2. Again, taking the minus 1 over 4 outside the square brackets, leaving cot 4t inside. And cotangent means 1 over the tangent, so this is like minus 1 over 4 times 1 over the tangent of 4t between 2 and 1. So now we can put our limits in, and this equals minus a quarter, putting the top limit in, 1 over the tangent of 4 times 2 minus 1 over the tangent of 4 times 1, which equals minus a quarter, 1 over the tangent of 8 minus 1 over the tangent of 4. And again, making sure that your calculators in radians, you should be able to confirm the answer in the textbook. Looking at part B, we've got to find the integral between pi by 4 and pi by 2 of a function that's a combination of sine and cosine waves. And I've plotted the function underneath, and you can see the function. Notice it is periodic, although I haven't actually carried on the function to make it obvious. But if we look at the function this point to this point, it continues from that point onwards. So it's periodic from this point, the second arrow that I've drawn on here. That means it repeats. It's just a more complex wave function, I think we can say. And actually, next year or the year after, you'll be looking at Fourier analysis, which splits up complex waves like in this diagram into a combination of sine and cosine functions, as in the integral we've got to do. So it's not uncommon to find integrals like this to have to calculate. So what we do now is we just integrate each part separately. So if I take this integral between pi by 2 and pi by 4 and perform the integration, then what I do is I say that equals, let's do each one in turn. So the sine becomes minus cosine, and the 2 comes out, so this becomes minus 3 over 2 cosine 2x. The second part, cosine becomes sine, and the 3 comes out and goes underneath, so it remains 2 over 3 minus 2 over 3 sine 3x. Between the limits pi by 2 and pi by 4. This time there's no constant we can take outside the square bracket, so we just now plug the numbers in, putting the limits in pi by 2 and pi by 4. So it's a bit more of a complex one to set out. So this is going to equal, using curly brackets, we put the first value in, so that's pi by 2 minus 3 over 2 cos pi by 2 minus 2/3 sine. So it's 2 pi by 2 here, sorry. And this is 3 pi by 2 minus, and then you put the bottom limit in, minus 3 over 2 cos of 2 pi by 4 minus 2/3 sine 3 pi by 4. So we just got to be careful that we follow through logically to get the answer at the end. So we can take the next step, so that equals minus 3 over 2 cosine of 2 pi over 2, which is the cosine of pi, minus 2/3 sine 3 pi over 2, minus 3 over 2 cos 2 pi over 4, which is pi over 2, minus 2/3 sine 3 pi over 4. And now I get the calculator out and put the numbers in, and this should confirm the answer in the text. Not forgetting the calculator must be in radians.